Okay, and we're back for a second session of Powering the AI Stack. Super excited to be kicking off this great conversation. We have an amazing guest today, but I guess I should start with, I'm Ilya Tabakh, and my co-host.
Hi, I'm Barak Turovsky.
Before we fully jump into it, I think it's great to actually get into what the kind of framework and the basis for our discussion and powering the AI stack is. And so, in the previous episode, we described kind of the 4Cs framework, how we can divide all of the noise and things that are going on in this crazy space. And so just a reminder, we're breaking it into consumption, cognition, compute, and capacity. This framework will help us, kind of divide this conversation going forward. Today, I think we're going to be focused on kind of cognition and compute, but there's some pretty fun news and things that have happened here over the past few weeks since our last episode that are kind of relevant here. Barak, I know you were talking about some interesting demand and compute things. So you want to share that with us?
Yes, I want to share it in the context of another thing that is important on our framework is to emphasize the mismatch in timelines and just to remind everyone. And that's where I think it's so important to deeply understand each component because the consumption is very fluid, right? The consumption could change a matter of days or weeks today, right? In terms of AI applications and demand for compute. The cognition, the models are developed in a matter of months, right? It's becoming way faster. Compute, AI infrastructure on a data center, this is a longer time frame. It's years, 12 to 48 months. And most importantly, that's the thing that was epiphany even for me, being in AI for many, many years, is that the capacity, the actual electrical grid and anything around it, the cycle is longer, way longer. It's not only, 4 or 5 years minimum, but it could be even planning cycle is decades. And this is so important for every AI practitioner. For example, I recently switched to a new role. I'm now Chief AI Officer at GM. Obviously, we will need to look at the huge scale across, autonomous and helping across doing AI manufacturing and all those things. So this planning is so important. And just to make sure you understand how demand fluctuates, we are getting all this news every day. From one end, Google basically says AGI is getting closer and closer. Everybody were talking about this, email from Sergey Brin to Google DeepMind that, hey, AGI is coming. And if you only apply more compute to train more powerful models, we can get to it very quickly. Please work harder. On the other side, we have all the DeepSeek phenomena. Oh, you don't really need it. Oh, you don't really need a lot of compute because there's powerful models that don't need a lot of compute. The point is that probably both sides have some validity to it. Both points have some validity to it because there might be different use cases. But you need to make these decisions now. And if you make a mistake, it's a very costly and timely mistake. So in that regard, that's why Ilya and I are very excited to bring great guests that will help us understand the space better across the entire stack. And today I'm extremely excited that we have an old friend and ex-colleague from Google, Vinoj Kumar, who, I'm laughing sometimes that I sometimes have this feeling elder or deja vu, that a lot of things that are being discussed like distillation and models. We worked on this at Google 10 years ago and people were rolling their eyes. How is that relevant to me? It's only for Google. I think Vinoj probably has a similar experience because we worked at Google to start first custom hardware that was made available, and he built the data centers to make custom hardware TPUs available. And at that time, a lot of people were rolling their eyes and saying, oh, why do we need it? And now every big hyperscaler is developing custom chips. So Vinoj did that many, many years, I think 15 years at Google, then basically ran AI infrastructure for cruise and automotive space, AI infrastructure for a couple of startups. So he's probably one of the most renowned experts on those topics, and we are very excited to have him on our second episode. So welcome, Vinoj.
Thank you for the kind words, Barak. Super excited. This topic is close to my heart. Back then, even now, a lot of interesting stuff is happening. Pretty excited to be here.
Yeah, maybe I'll jump in with the first question, Vinoj. I just want to kind of set the stage. Let's start with the growth of AI and data centers. Can you touch upon kind of power, hardware evolution and kind of cooling infrastructure? How did things develop?
Yeah, let's start. Actually, that's a great question. Let me put AI in perspective in terms of growth and scale. If you look at AI compute, that's grown at an unprecedented rate, right? For instance, AI training compute has roughly doubled every 6 months since 2012 and growing at the rate of 3,000% in the past decade. On the power consumption side, modern AI clusters consume, we all know, 50 to 100 megawatts, right? Especially with large language model training, they consume 1 to 2 gigawatt hour of power. Same thing's happening on the GPU utilization as well. What used to be 20-30% now has increased to almost 70-80%, depends on which hyperscaler you talk to. And that's a lot has to do with multi-tenancy, containerization, and better optimized frameworks. So utilization is going up and up and up, right? Which is great. The other important thing is memory utilization, because a lot of them are based on one domain architecture. There's a lot of memory access, and the memory bandwidth is super important. That's growing at a phenomenal rate too. And today we see it at 2+ terabytes per second, right? We can get into a little bit deeper into that one.
Yeah, it's a great point, by the way, Vinoj. I mean, you probably remember that there was a lot of people that didn't even understand that for inference, you need way more memory than anything else. And right, and even that, when TPU was developed, was a big, non-trivial thing. So it's a really important point that you're making.
And also, speaking of which, cooling infrastructure, these GPUs are very power hungry. And if you look at the cooling infrastructure, right, a typical rack for the GPUs, for example, consume 4 to 8x more power per rack compared to traditional one. So which means it's almost, if you look at it, the adoption has grown, like liquid cooling has grown more than 50%. That's another trend you would see, right? And this kind of demand is also forcing people to look at more carbon aware scheduling, more carbon neutral alternatives. You'll see a lot of companies kind of reusing heat systems and stuff like that, right? So that is sort of where the current landscape in terms of the growth is hunger is, right? And if you were to peek into the future, you're going to see a lot of distributed training happening across the geographies. That's one thing. And also, for example, because you need feed and speed, optical interconnects, they're growing at a phenomenal rate. So that is sort of, to answer your question, Ilya, that's where we see.
Yeah, and just to pick on the sort of liquid cooling, from like the capacity and utility side, about 50%, maybe 45% of the power in a data center goes to cooling today, or at least that's kind of the high level estimate. And so what's interesting is as you get into that 40 to maybe 60 kilowatt a rack density, air cooling, and sort of the traditional approach is no longer sufficient. And so, as you mentioned, kind of direct to chip liquid cooling or maybe immersion cooling. And what's crazy is that people are already talking about rack densities that would require not just liquid, but maybe refrigerant, right? Because you have so much heat that you got to move. Now, you can't just start with normal room temperature water. You actually have to bring cooling to the chip. And so it's interesting to get kind of the practitioners and the architects talking to the utility folks, because they don't really realize that kind of interconnection. So I'm glad that you pointed that out.
So Vinoj, just to go a bit deeper into the compute part of the forces equation, how do the AI workloads differ from traditional workloads, and how do those requirements influence system design? Because even that is very non-trivial thing, right?
Yeah. That's a great question. So when you look at, like, for example, traditional computing, we're talking about like web servers and databases and stuff like that, right? Let's look at the characteristics and how they're different from AI workloads. First off, in most traditional compute, it's sort of sequential. There's a clock and things happen in sequence, right? When it comes to AI models, for example, they're massively parallel, right? That means you need a lot of simultaneous matrix operations. That's a given, right? This means you end up using a lot of specialized hardware, GPUs or ASICs, which are very specialized, which are very good at making matrix operations. This type of architecture is also driving a lot of heterogeneous custom architectures. That means specialized for certain type of things. Again, it goes back to the power. The metric you want to measure is how do you improve efficiency? That means how much work can you do per watt, right? So that's the goal here. That means consume less power, generate less heat, and do more work. That's what going. Again, goes back into liquid cooling as well, right? You cool, how do we cool these things? Secondly, you want the parameters. All these models are getting larger and larger. They have to fit into memory. So you need large memory. And high bandwidth for the memory.
Are you talking right now mostly training, or because
I'm referring to training, because that's a bigger,
right? We didn't even get to inference, right?
From the training side of things, they have to fit, right? Similar choices, for example, if you want to move memory, HBMs are becoming, right, for example, very prevalent, high bandwidth memory. So this memory sits on the interposer very close to the core, so you can move data in and out, right? Because you have to have parameters moving in and out for the computation. So they're evolving at a fast rate as well, because you need that level. Now, if you look from a data handling perspective compared to traditional workloads, it's very iterative, right? You run multiple iterations, then you have to do a lot of checkpointing. That means you need to have a lot of high throughput data access. So your storage architecture needs to support this high throughput IOPS, more than latency in the case of training. Of course, in inference, there's a lot more inference effect. That's why you see a lot of choices in terms of NVMEs, SSDs, STFEs, HDFS file systems with SEP, those kinds of things. Distributed architectures where you can have no single node can bottleneck. A very interesting issue on the networking side as well. If you look at the networking fabric and if you look at the networking flows in a traditional network, they're very high entropy, what we call high entropy flows, which means they're distributed, the flows are, and they don't utilize full bandwidth, right? However, in the case of when you do machine learning, there's a lot of collective operation that happens, right? Because everyone computes, suddenly there's a collective operation that happens. So you see a lot of low entropy flows. Certain links get saturated, very high bandwidth, but the flows are not contiguous.
Very, very important. Yes. I think you mentioned to me, I believe it was either you or someone else, that Jensen specifically says that networking is one of the biggest bottlenecks in the data center design, right? And I don't think people fully understand it. Obviously, NVIDIA does. They both, acquired Mellanox. They also just announced an additional phase of this partnership with my previous employer, Cisco. But it's very, very important topic that people don't fully realize.
Yeah. So that's why there's a lot of topology that changes. You have a lot of network experts over there. For example, in traditional networking, you use what's called a fat tree, a leaf spine topology, right? Because there's only north-south traffic. Here, you use one type of topology for the north-south traffic where you're bringing data in. And when the GPUs compute, you're going to have a very high-speed networking connectivity on the east-west traffic. That's where you end up using like NV switches. And then also your oversubscription is going to be low and you have different types of topologies over there.
And that basically impacts the speed of training, right? To oversimplify it, right?
Yeah, because you want the nodes to be communicating very fast on the east-west side of things. That's where all the technology.
Yep. And energy probably, if you're not fast enough. Yes, makes sense.
Yeah. So people are experimenting with all kinds of like Torus and something called Hypercube and stuff. These are various technologies which are different. Because of the workload that you have, right? It's very critical. The other one is also in terms of fault tolerance. For example, in traditional networking, if a node goes down, you come back up, it might take a few seconds, few minutes, in the sense that it's not as expensive as when it comes to training. For example, if a node fails in the case of training, you have to go back to your previous checkpoint and redo the iteration again, right? Because even the one node that's falling behind causes disruption in your training. So you got to make sure when you build these high-speed, low-latency network fabrics that you take care of the fault tolerance, kind of take the node out of the picture if something's failing, stuff like that. So we can get into a lot of the software stack observability, but that's one of the focus you got to do.
In general, before we dive too far in there, one of the interesting things I think to observe that I didn't even realize that there's sort of these phases, right? There is the populating all the memory to do the computation. Then there's sort of the computation. Then there's sort of the sync. And if you sort of unexpectedly either lose a node or have a power outage or anything like that, there's sort of this startup and shutdown. And in power generation, it's actually the same thing, but nobody really ever thinks about it. But here it's kind of an interesting thing. I don't know that we need to dive into it now, but just kind of mapping that out for the big, sort of loading memory, doing the compute, syncing. It looks a little bit different for inference than for training, because of, you pointed out in our pre-discussion, kind of back propagation versus not. And so it's really interesting to maybe map that out sort of generally and think about what that means for all of the different parts of the 4C.
On a super high level, what are the big differences between, again, one of the reasons that TPUs initially at Google, it was so important that Google, and now people discover that inference is slow or expensive. Google discovered it, 10 years ago and had to do something about it. So what are the big differences between, by the way, just for historical context, when we launched first LLM with Google Translate, the training slowness was not such a big deal in that particular use case. And the reason is because languages translation do not change overnight, right? It's not like search. So, but what we were really stuck was actually inference, because inference was 100x, was crazy, 100x slower than production. So, Vinoj, like on a high level, what are the main differences in architectural needs for inference versus training.
Yeah. So the difference, for example, if you look at the inference, and I think you mentioned, Ilya mentioned, like, for example, you don't do back propagation as much. In that sense, the GPU computational power is required is less compared to training, right? On the other hand, on the inference side of things, it's very latency sensitive. When you get a request, right, you're going to parse the request, then the model runs, the model has to load, you run, you get the results and push it back, right? So when you have a lot of requests coming in, goes back into like a traditional web architecture where you have a lot of front ends. It gets fanned out to your back end running the models, and you have to run. So one of the things, for example, in one of the startups we ran into is when we had high number of inference requests, especially this was video processing, the time to load up the model was very time consuming. That means you're loading up the parameters, loading up the model. It took a few minutes. So even though, for example, your infrastructure was built on Kubernetes, containerized, you scale up, auto scale up when you have a number of requests coming in, the startup time took a few minutes, several minutes, that it would actually impact your inferencing. So you got to figure out architectures and how am I going to do that? How am I going to cache that? Those kinds of things.
One comment, I don't know if you guys trying in a piece of additional news and how it's related to latency. And we kind of dealt with it at Google Translate as well many years ago. That I don't know if you guys tried the deep research feature of ChatGPT. I recently tried it. It's amazing. You should try it. But one thing to me, as doing it for many years, it's a very clever way to deal with latency. Because instead of saying, hey, I will do a bunch of things and respond immediately, they're saying, oh, wait, and I will notify you. And you know what? For many research projects, legal research, or whatever, I always say it's totally okay to wait, maybe even half a day to wait because you compare it to multiple days of research. But I think it's a very clever UI trick. As an example, in Google Translate, we literally measured how much delay people will tolerate because we knew there'll be some delay. And then initially, as I said, it was 100x. We measured it up to 8x. Then production, and people were okay. 4x, they were okay. We ended up to be on 2x with TPUs and distillation. But it's very important to understand how there's multiple ways to deal with it, but the real basic way is to basically improve the architecture design and everything around it to make the latency faster.
To that point, actually, if we're talking about the architecture, people are working, for example, optimizing models, for example. So what they do is that because the model has to fit in, now in the case of inference, especially if you're running at the edges, that's one of the ways you can do, right? In order to reduce the latency, move the compute closer to where the user is, which means you have to be on edge devices which have less memory. So if they have to have less memory, the model has to fit. So people are optimizing ways to figure out building more optimal models. For example, there's a company called Neural Magic that they did a lot of pruning. In other words, they had that run time, you went through the model, you prune the model, so you make it smaller, tighter, more efficient. And if you look at our colleague from Google, like Modular, they're optimizing. They built Mojo, a language specialized, which is optimized for ML, and also a runtime that's focusing on the inference side of things.
Use case is different. Not every use case needs very low latency, and it's very important to understand it because super fast latency is expensive and energy demanding, but we also need to understand current expectations. A lot of use cases, search, networking, you name it, people expect very fast response, and that's why those use cases are way more complex. But yes, please keep going, Vinoj. It's, as I said, it's a very, very important discussion that loads, distant memories from previous life.
Yeah, so that is pretty. So that gives you hopefully give you a preview of how the workloads differ and how the design changes.
This is a good sort of opportunity to really zero in and dive in on the evolution of the hardware. We're already kind of touching on, GPUs, TPUs, FPGAs, and custom hardware and things like that. But let's dive into some of the things that are happening in the data center. Things like, the rise of specialized AI accelerators, distributed computing architecture. We've already kind of started covering some of them because you can't take away the pieces that run this stuff without, talking about how it works. But let's dive into a couple of those and see what you're kind of paying attention to, Vinoj.
Yeah. So I mean, even today, I think GPUs are still the workhorse for the data center, right? But we are also seeing a rise of specialized AI accelerators like ASICs and FPGAs. And there are companies, for example, leveraging FPGAs. So as the algorithm changes, you can use FPGAs to build custom hardware, in the sense, customize it. So you can get the speed and efficiency of hardware at the same time adopting to software, right? That's one of the dangers, because if you build hardware that's very specific to software, if the algorithm changes, transformer evolves, then you're stuck, right? So that's one of the challenges. So you see a lot of, kind of push towards FPGAs as well. Again, depends on the use case, the workloads. Speaking of GPU as a workhorse, for example, you see NVIDIA H100 GPUs, they're almost like, speaking of inference, I read somewhere it's 30x more performant compared to A100 for inference, right? So it's doubling, it's going at a phenomenal speed. Speaking of ASICs as well, for example, AWS has the Trainium. So there are some domain-specific ASICs, like I said, very specialized for certain types of workloads where you can leverage them a lot. You see that a lot. In terms of where it's heading, like I said, memory bandwidth, same thing. They're doubling memory bandwidth with HBMs. And we didn't talk about disaggregated memory. That's another. You'll see data centers evolving to where, because of the distributed computing nature, memory is disaggregated, and people are using like GDDR or CXL technologies to actually distribute storage. Leverage that, right, for disaggregated storage. Same thing, HBMs. If you look at the generations from 1 to 3, the bandwidth is almost, going at 50%, evolving at a 50%, more than 50% rate. There's a software side of things. There's a lot of parallelism that's happening, right? People do model parallelism, or, using cluster networking. That means, how do I have very large distributed set of nodes, parallelize it, underlying architecture with InfiniBands and RDMA. I can have very low latency, high-speed net interconnect, which means I can put a wire between the nodes, and which means I can build, I'm going back to the training again, or even inference for that matter, right? I can utilize the compute that I have, right? Remember, there's a wire between these nodes. The faster you can build them, you bring them closer, take away the bottlenecks, you can leverage the cluster networking, right? Optical interconnects are being explored too. They're getting closer to the chip. I see some, for example, there are a lot of startups in that area. You're going in that direction as well. We use, for example, Google kind of pioneer at that time, doing a lot of optical networking at the data center level, right? Even from, again, it came to a cost issue. Server to the top of the rack switch, to the switches. Where do you put copper versus where do you put it's a trade-off, right? Cost versus the speed kind of thing. Now you see a lot more optical connects getting closer and closer to the machines themselves.
I'm not just curious from your perspective. Speaking of, the goal is ideally to try to reduce time between, again, you have a very fluid demand, and anything below starts to be longer, right? So you have a model which is, months to years, and that shrunk. Data center design was taking years. What are in your opinion, what are still the biggest bottlenecks, the areas that are kind of holding up to make it, ideally it's as fast as possible, right? I don't think we can get to data center design in a matter of a couple of months, even though, Elon Musk put up data center, broke bunch of rules, etc. But I'm just curious, what do you think are the biggest bottleneck to track that, innovation in that space could be really important to speed up data center design?
That's a very interesting question. Actually, if you look at how long it takes, what it takes to build a data center, right? First, you have to get a space. You have to find that space, it's building construction. You get space close to power, then you have to get power. That's the most important thing, right? Because the megawatts of power, you have to work with the utilities and everything else to get the power. Then the shell goes up. It's a construction time zone. And then you're going to populate, inside, once the IT infrastructure is in place, for example, power and cooling is in place, then you move the racks in, do the wiring, and then the software up, bring ups, etc. So if you look at this timeline, it takes almost like 2 to 4 years for a very large data center to happen, right? People are trying to shrink that. And the way we do with modular engineering today, some of the ways where you can optimize, if you look at that workflow and say, hey, where do I optimize? How can I do it faster, right? And also you need to keep in mind, depending on your workload, if it's inference, for example, you need these edge data centers closer to the user. That means high urban density, right? Which means you have to find space, colo spaces, stuff like that.
And you need to find grid, right? Yes, by the way, that's a great point. And by the way, just a heads up, and to make sure people wait for these questions, there was a question that is very relevant to what you just said. The question is, and we'll address it later, but can existing traditional data center be converted to AI-focused data center, or do new facilities needs to be built? We'll address it, but it's just kind of rhymes with what you said. Go ahead, Ilya. I think you had a question that you wanted to ask.
I love the conversation here because a lot of the kind of interplay between what's the application, as we're getting into these multimodal models, as we're getting into sort of moving maybe video or, kind of heavy images around, you get a very different type of topology that's necessary to convert. So I just wanted to bring up that, for example, in the telecom data centers, they've had to do a lot of looking at, how do you increase density because they're not sort of building as many new data centers as they might otherwise. And so there are some things that you can do to sort of retrofit, but it'll be interesting to sort of jump into that discussion here in a little while.
Yeah, let me just touch upon that. You'll see a lot of for example, a lot of the companies that are focused on crypto, for example, when the crypto is shifting, they're moving into the AI, ML optimized data centers. And what they're finding out is retrofitting is not that easy. For example, goes back to your cooling infrastructure, for example, and how the data and the networking infrastructure pretty much you have to rip. Like I described, your fabric infrastructure is going to be slightly different. Your your cooling infrastructure is going to be different in terms of getting liquid cooling close to the GPUs. So sometimes people are finding, hey, it's much easier to rip everything out and rebuild it in the sense. Another important thing I'm also finding out is because of the thirst for power, people are exploring ways where you can move the compute close to where the power is. For example, if you go to areas like North Dakota or Texas, where there's abundant power at night, it's a diurnal pattern, right? Power is not used at night. Utilities actually pay you sometimes to use it. So the idea is, hey, if I can build a data center close to that and move my training and build an infrastructure, software infrastructure and hardware infrastructure, so I can do like training at night in a location where it's cheaper, and during the day I do something else. So people are exploring that options too. So people are exploring with container-based data centers as well, close to where the power is, like the Dakotas and Texas and stuff like that, right? So again, it's difficult. It's easier said than done because operationally it's a lot of burden. We'll see how that has to evolve. That can evolve.
Yeah, and I think even like everybody was talking about the DeepSeek moment, right? I think that ratio between what percentage of your time is going to be spent on training versus inference is really going to inform. I actually had a distributed data center company where I was deploying modular data centers in weird places. In the US, at least, there's a lot of places where there's a lot of wind energy and things like that deployed. That's going to be structurally, pretty cheap, or you might even get paid for decades. There's a lot of really interesting kind of power things, but that doesn't always overlap with the backbone network latency and things like that. And so it's a really interesting balance there, because like there's companies like Caruso that are doing amazing things at, the edge, almost in oil and gas fields, right? But there traditionally is not a strong network backbone to West Texas.
Correct. You get connectivity to, kind of tap in to move data in and out, because people traditionally have it like in either Amazon S3 or elsewhere, right? Great point.
Those are really, I love this discussion, as I said, if we can really deep go, etc. So Vinoj, switching gear a little bit, as I mentioned, you have amazing career at Google building those data centers long before that everybody looked at that. As I said, people probably were looking as it's a commodity. Why do you need custom hardware, etc.? And Google obviously deserves a lot of credit investing early on that. There was multiple. I distinctly remember when we introduced TPUs for translation. To me, it's a DeepSeek moment at that time, because they introduced the papers that say, we can do the same powerful model trained on CPUs. And we would going crazy declaring code red and looking at that. And yeah, it was pretty powerful. But I think eventually it's actually slowed down maybe some of the innovation on the chip side for rest of the industry, because people said, we can do it cheaper and easier than, developing custom hardware or even using GPUs. But switching gears and talking about your amazing experience on autonomous, which it's another humongous use case that requires a lot of compute, edge, etc. So what are the biggest differences in infrastructure requirements between general AI application and specialized domains like, let's say, autonomous driving?
That's a great question. So let me split that into the sort of inference part and the training part, two different dimensions. On the inference side, because, for example, in autonomous vehicles, you can think of running an inference because you're doing perception, prediction, planning, right, while the vehicles are moving. The difference is that in general application, you can tolerate latency in seconds, perhaps, or even minutes and not notice it, while in autonomous, it's sub 20 milliseconds, right, response time for safety critical situations. You have to make decisions very fast. So that means your compute, your inference has to be really, really fast. Typically, like autonomous driving systems have dedicated hardware. And also you have to deal with sensor fusion. You have data coming in, multimodal data coming in from various sensors. So you should be able to handle 1 to 2 terabytes of data in real time, compared to batch processing. That's one of the issue, right? Latency and real-time processing, how you do. The second biggest one is reliability and redundancy. For example, in autonomous systems, you got to be like 6 9 7 nines reliability, right? Where with traditional systems, single 9 2 nines you can tolerate. That's a key thing. You've built a lot of redundant systems, both hardware and software, and fallback systems. If the vehicle doesn't know what to do, it dials back, and there's a remote person who actually takes control of the vehicle and say, hey, if the model can't handle it or the vehicle cannot handle it, let me pull over, or some safety mechanism getting built in, right? So that has to be part of the system that's built in when you talk about this. The other one is I can think of is the environment adaptability, right? For example, if you think where the autonomous hardware needs to be running, extreme temperatures, minus 40 to 100 plus degrees, where Arizona to Minnesota, right? And also they should be able to withstand shock, and it's not like a controlled environment in the data centers. So whatever cooling solution you build in both your physical hardware, cooling infrastructure has to be very, very robust to be able to kind of live in that rough environment, as an example.
Very, very fascinating. By the way, this is very important for people to understand in their domain what it means. Maybe, I don't know, if there's additional tidbits. I know you did, AI for defense sector, etc. Any additional things that are, unique or different from the domains or industries that you worked on or supported that is important to call out?
Yeah, so defense, actually mentioned defense, that's actually an interesting application too. For example, if you look at defense industry applications, we do a lot of object detection, object classification, like drones, for example. That means you have, so one of the challenges there, what happens is that your model, let's say you train for object detection, detecting ships or enemy tanks and stuff like that. You train the model and you deploy them. But what happens, you have a lot of divergence or data drift that happens. For example, your data, let's say you don't have enough data for cloudy weather. And when the drone goes off, it's a very cloudy weather. You start seeing drift. That means you're going to get a lot more false positives or false negatives. So you need to build a system where you recognize, oh my God, the data is drifting, what's going on, update the model, retrain the model, and put them back into production very quickly, right? Because these are edge devices. Or for example, combat troops have these edge devices. They're using AI to detect, send a kind of drone in front to see what's happening on the enemy side of things. And if the scenario changes, which you're not trained, you have to adapt very quickly. So there, for example, your infrastructure to actually fine tune it, test it, redeploy it has to be built in. That's where the software comes in. Again, also for example, your infrastructure to actually, kind of detect that there's a drift that's going on. There are different types of drift. There's data drift, there's model drift and stuff. You know more than I do, Barak. So in order to be able to detect that, alert someone, either human in the loop or automatic fine-tuning, take the data set is another difference.
Yeah, no, those are great point. And for AI practitioners in the audience, and also frankly for, investors, it's really important to understand that piece, because at the end of the day, on a very basic level, it's like, accuracy demands, and that will drive potentially size of the model, and latency demands and other components will drive a lot of considerations on cost, right? And speed to market, and you name it, how much compute you need. So it's really important to understand it and get a perspective on that. Like, what if there are any unique characteristic for your domain that might impact down the stack on compute and maybe even capacity level. So I think I love those discussions, and I always learn something, because there are so many domains, and there'll be so many more domains where AI will be applicable.
Just to actually pull on that string a little bit, one of the fun parts about data centers is they're so observable and so controllable, is that's actually gotten pushed all the way out to, can we sort of think about what the power cooling systems are doing in response to that workload, right? So as you start to deploy 100 racks at 50 or 75 kilowatts a rack, if all your stuff's happening in one rack, but not on any of the other racks, right? There's sort of a little bit of a physical distribution part. Like very much back in the day, there was the hotspot or the fireball on the Intel Pentium chip. There could be the same thing that happens in a data center floor, right? And so just kind of pushing that thought the other way is, as you sort of do the software, do the architecture for it, you can also control sort of the physical plant and the mechanical systems. Even to the point, if you understand that, hey, we could turn down or maybe turn on our backup generators for 15 minutes and we'll be okay, but it's important for the grid, that actually opens up a whole other kind of capacity conversation on how this data center connects to that power and utility infrastructure.
Yeah, that's actually a great point to touch upon that, especially when it comes to, for example, you probably have a segment on capacity planning, because this is, burst capacity planning is pretty important too, because your workload suddenly bursts up, right? Both in training and inference. And you have, for example, a lot of nodes failing. You need to have a lot of observability built in, both on the infrastructure side of things, or it could be in the NCCL library. So observability at every level in the stack, you detect something's happening, because like you said, even if like a single node that's slowing down could actually impact your training, right? That means your efficiency goes down, cost goes up. Then you have to bring in nodes. You mark that node as dirty. Then you bring up a whole bunch of nodes, stuff like that. So you got to have a lot of fluid, both power and compute to actually be efficient.
No, that's amazing. And we've covered a lot of ground. We have a few minutes left here, so hopefully we'll get another question or two from the audience. We already kind of jumped into the kind of traditional data center retrofits. I'm glad we got a chance to dig into that. But I guess as my last question, do you think kind of GPUs or custom hardware is going to be kind of a key bottleneck going forward, or how long, or not? Like there's so many moving pieces here. It seems like the accelerators are very visible, a lot of sort of demand and queues, and you have to reserve for a long time. But do you think that will be kind of a key bottleneck going forward?
In the case of GPUs, so we hear a lot of, for example, the supply chain side of things, right? GPUs being the bottleneck in the sense where there was a huge demand. For example, NVIDIA had trouble supplying it. So supply chain is important consideration too, because everyone's kind of going after the same, way for TSMCs and stuff, supply and demand type of thing, bottleneck. Other question is that as the workloads evolve, as the models evolve, whether GPU, which are sort of general purpose in a way, would they lose share to custom hardware? Because we see a lot of chiplet based design, for example, D matrix. There are different types. For example, we talked about inference. If you look at D matrix, what they're trying to do is analog computing, right? Putting compute into memory, so that way you reduce that latency, right? The question is those type of companies, or if you look at Etched, they're doing a lot of photonics. So you have a lot of these third-party ASIC, startups attempting to solve this system problem in terms of whether it's supply chain or technology related in different ways. And if you look at Samba Nova Systems, their approach is configurable hardware, okay? So software-defined data center type of thing, where, hey, I can combination of ASICs and FPGAs and stuff, I can reconfigure it, not tied to a specific architecture. So you see, I think it's going to be an interesting balance to see how GPUs are still the workhorse, like you said.
It's so great to hear your insights, Vinoj, even when I ask you about, in data center, what's the bottlenecks. I think the key, one of the reasons that me and Ilya decided to do this podcast was that even I realized that, as you said, hey, in data center, there is a lot of physical stuff you need to do to even start talking about, deploying GPUs. One reason that we wanted to do it, we wanted to make sure people understand that it's way more complex ecosystem than just simple question, will GPU shortage will be faster or will ease up or not. There is so many other moving pieces that it's very important to understand. So I think, to me, that's a fascinating discussion to have, both on data center designs and everything around it that powers it, and obviously up to the model and application that will kind of impact demand. So it's a really good insights. Ilya, are there any additional questions that came our way?
Not yet, but actually, as we're, we got a couple minutes left, and as we're talking through this, one of the things, so this is funny because this conversation is really a flashback to my computer architecture days, right? And as Vinoj is talking about kind of the hardware capabilities, and then how do you sort of compile and run these things efficiently on the hardware? And then what do you do in software? One of the places where I've spent actually a lot of time recently is just the raw hardware capability doesn't mean that you're going to have a higher, and so I think even at the hardware software interconnect, even if you have two GPUs, that this GPU is faster, but this GPU has a better compiler and it can be used more efficiently. And you, Barak, pointed out that, NVIDIA has a very tight sort of look at hardware or network integration. And even in sort of CUDA and in their software stack, the utilization of that network all the way through to the programming layer. I failed until, probably the last month and a half or two to really appreciate sort of how that's developing. And so as these sort of facilities scale and have a lot of bandwidth, and to Vinoj's point, for a lot of these new hardware sort of things to come up, it's going to be really interesting to see sort of hardware horsepower versus compiler efficiency versus the ability of, sort of the software developer to use it.
Yeah, and by the way, that's a very important point, Ilya and Vinoj, because NVIDIA is actually very smart about it. And to your point, they look both down the stack, but also up the stack. They're very engaged in model developer ecosystem and trying to basically understand and support all novel model development tactics, because they also want to help and understand how to more efficiently run this model, both on training and inference side. I think it's a very smart move, but it just reiterates your point. And sorry, Vinoj, I see.
No, to your point, we touched about, we focused mostly on the data center hardware side of things. We didn't. The software stack is super important, right? Like you talked about the CUDA libraries and the optimizations that need to happen in order to leverage the hardware underneath. And you're right, NVIDIA has a very strong ecosystem, and that's what's driving the adoption. And moving forward, it's for other startups to dislodge is going to be interesting to see, right, in which areas they can actually find the niche.
Yeah, the opportunity that I kind of see in that, though, is AMD and folks are doing a bunch of stuff with ROCm and sort of their ability to interface. And then what's cool is once you actually have all this stuff at the orchestration level, you could write, more intelligent compilers where people are writing in whatever, right? And you can sort of specialize it for your hardware. But that's very hard to do at sort of a, single application level. But at the aggregate level, you can do, much better decisions and maybe more targeted compiling and things like that. And I've seen a couple interesting startups pop in that are, starting to do sort of that analysis and sort of optimization to the hardware at kind of the aggregate level, which is great. So we have one last question and we have a minute left, so we're going to have to be very quick. The opinion question is, is AI here to stay? Or it's sort of, the statement is AI is here to stay, but cloud costs are cheaper initially, but they add up and will cost more, So essentially it's kind of the on-prem versus cloud conversation. Are people essentially going to go all cloud, some kind of hybrid, or kind of what's that going to look like going forward? That's always a fun one too, but that's a,
I think it's a separate.
Yeah, Barak, let me hear your. What are your thoughts?
I think it's like, nobody has a crystal ball, but frankly, first of all, thank you, Vinod. It's amazing session, amazing to hear and hear back, talking about the flashbacks that you and I chatted, I think, way before it became so hot. But I think every time I meet with folks like you, I feel we're just barely scratching the surface. There is so much stuff to talk and it's moving so fast. But again, the key for us is also to highlight the timing mismatch. Some stuff moves very fast, some stuff moves slower. And it's very important to be prepared and be very practical about it on every level of this 4C stack. So thank you again, Vinoj. Thanks for everyone who listened to it, and stay tuned. We'll have more amazing guests for future episodes.
Thank you guys. Thank you, Barak. Thank you, Ilya. It was fun.
Thank you.
Indeed.
Bye-bye.
Thanks a lot.